Hello everyone, welcome back to this online class. Today we are going to look at the method of power series as used in solving linear ordinary differential equations. Now we have this problem. We are asked to find a series solution in powers of x for the following differential equations. In part A, we have x squared plus 1 times d squared y over dx squared plus x dy over dx minus xy is equals to 0. In part B, we have 2x squared times d squared y over dx squared minus x dy dx plus x minus 5 times y is equals to 0. So this is a case of a general power series. I want us to take note that when you talk of a series in powers of x minus x naught, you can take note that a series in powers of x minus x naught takes the form y is equals to a naught plus a1 x minus x naught plus a2 x minus x naught squared plus a3 x minus x naught cubed plus so many other terms. And this can as well be written as y is equals to the sum from n is equals to 0 to infinity a substitute n times x minus x naught raised to n. And usually n naught is not equal to 0. So these are series in powers of x minus x naught. But if you look at the equation, we want a series in powers of x. Look at what we have in powers of x. So if I want a series in powers of x, I'm going to substitute x naught is equals to 0. So you can write here to find a series. That should be series. To find a series in powers of x, we substitute or put x naught is equals to 0. So that's the idea, that the x naught here must be equal to 0, so that we'll have a series in powers of x. So now let's look at part A. Let's see how to solve it. We start with part A. So you write here part A. Now, even before you solve it, you need to know whether this value of x naught, is it a singular point, or is it an ordinary point? So you can say that the point x naught is equals to 0 is an ordinary point of the given ODE. I believe you know how to find ordinary points and singular points of any given differential equation. You see, when we substitute 0 here, where we have x squared plus 1, we are going to get 1. When you get a number different from 0, then that point is an ordinary point. But if suppose I will have gotten a 0 here, when I replace x naught, then you will have said that that value of x naught is a singular point. So in this case, it is an ordinary point of that given ODE. So we are going to say let the solution be, let the solution y is remember y is a function of x. let it be equal to the sum from n is equals to 0 to infinity. Remember, we are substituting x naught is equals to 0 here. So we are going to get an x raised to n. And the requirement is that a naught is not equal to 0. Remember the a naught, a1, a2, all the way up to an, up to infinity, I mean, those are series coefficients. They are called series coefficients. So we can just say here, I can comment here that a naught, a1, a2, all the way up to the last one, these are called series coefficients. So let me just bracket this and talk about it. These are series coefficients. Remember, they are constants. Now, we are saying let our solution be y is equals to the sum from n is equals to 0 to infinity of a subscript n times x raised to n. Let it be the solution of the ODE in part A. So I need to know the first derivative and the second derivative, because when you talk of a solution of an ODE, it is simply a function that satisfies the differential equation. So if I get the derivatives of that function and substitute into the given ODE, we will be able to satisfy the ODE. So let's get dy dx. So you can say therefore dy dx. What will it be equal to? It is the sum from n is equals to 0 to infinity of, remember, we are using power rule to differentiate x raised to power n. That will give us n a subscript n times x raised to n minus. I've used power rule to differentiate x raised to n. An is a constant. So look at what we have found. When you put n is equals to 0, the result will be 0. So this thing can as well be written as, we now need to start from n is equals to 1. Because the first term of this series is 0, which does not, you see 0 is nothing. So there's no harm when you start from 1 to infinity of n, a subscript n, x raised to n minus 1. I hope that is clear why I'm shifting from 0 to 1. Because you see, in this series here, the first term will be 0. So 0 plus anything is the same value. So that's why we are shifting it to 1. So that the second term going onwards are values different from zeros. The second derivative, d squared y dx squared. So we are differentiating this one here with respect to x. Again, use power rule. It will be the sum from n is equals to 1 to infinity of n minus 1 an times x raised to n minus 2. Power rule of differentiation. Again, look at here. The first term of this series, if I put n is equals to 1, I'm going to get 0. So the first term is 0. So I can start from n is equals to 2 going onwards. So this is the same as writing the sum from n is equals to 2 to infinity of n minus 1 a subscript n times x raised to n minus 2. I hope you know why I'm shifting from 1 to 2 in this case, because when the first term is 0, it is better you start from the next term. It's still the same. See, when you say 0 plus a constant, another constant, you get the same constant. Or 0 plus any other function, you get the same function. So now that we have found the derivatives of the given function, which is our solution, let us substitute them into the given ODE. So our ODE is this one. ODE, it is x squared plus 1 d squared y dx squared plus x dy dx minus xy is equals to 0. So I need to replace the y and its derivative. Replace y and its derivative. So this simply means that we have x squared plus 1 times the second derivative is the sum from n is equals to 2 to infinity n minus 1 a sub n x raised to n minus 2, then plus x times the first derivative is the sum from n is equals to 1 to infinity n a subscript n x raised to n minus 1, then minus x times y. Remember our y was the sum from n is equals to 0 to infinity of a subscript n times x raised to n. And that should give us 0. So let us simplify. So you can just say, or I want to take this inside. Even this one, you take it inside. Even this. So when I take it inside, this is what I'm going to get. Or let's start by multiplying by x squared times this one. That will give us the sum from n is equals to 2 to infinity n into n minus 1 times a subscript n. Now what is x squared times x raised to n minus 2? That is the same as x raised to n. Then plus, now I'm multiplying by 1. We get the same series. N is equals to 2 to infinity n minus 1 an x raised to n minus 2. Then now, remember, I'm through with this. Now let me go to this one. When I take x inside, remember it is x raised to 1. So we'll have the plus the sum from n is 1 to infinity n a subscript n x raised to n. Remember laws of indices, x raised to 1 times x raised to n minus 1. When you take 1 plus n minus 1, you get n. Then the last one is the other series is now is negative. The sum from n is equals to 0 to infinity a subscript n x raised to n plus 1 is equals to 0. So 1 plus n, that's n plus 1. Now, look at those with the same power of x. So the next thing here is to combine the terms with the same power of x. So it's like we have here x raised to n. I can see another one here. So those are like terms. Now look at the first one. The first one is from n is equals to 2. And the other one is the sum from n is equals to 1. But I want to combine them. How can I combine those two, given that they are starting from different lower indices? This one is starting from n is equals to 2. The other one is starting from n is equals to 1. So what happens? Look at the one that starts from n is equals to 2. The higher value of n, you can revert it back to the lower value because it means the first term in this series here is 0. So there's no harm when I start from n is equals to 1. There's no harm because that means the first term will be 0 and it will not affect that series. So that this is now 1 and also this is 1. So now I can combine the two. So what we'll have here is the sum from n is equals to 1 to infinity n minus 1 plus n a subscript n x raised to n. Then the others I'll just retain them. So we have plus the sum from n is equals to 2 to infinity n minus 1 a raised to n a subscript n then x raised to n minus 2. Then the other one is the sum is a minus. So that should be a minus. The sum from n is 0 to infinity, a subscript n x raised to n plus 1 is equals to 0. Are we able to simplify? Look at the first series here. You can be able to work out this. This is the same as n. This is n into n minus 1, then plus 1. So this is the same as n into n minus 1 plus 1, which is the same as n squared. So I could write this as, or the sum from n is equals to 1 to infinity of n squared a sub n x raised to n plus the sum from n is equals to 2 to infinity n minus 1 a sub n x raised to n minus 2 minus the sum from n is equals to 0 to infinity a subscript n x raised to n plus 1 is equals to 0. So now what do we do? Look at the powers of x. They are different in the three summations. So what we do, I want to be able to transform these powers of x to a common power of x. Usually, you transform them to the power of x that is the lowest power of x. What is the lowest power of x here? It is n minus 2. What I do, I am going to change this from n plus 1 to n minus 2. So here I have to put, where there is n, I replace n by n minus 3 so that I can get n minus 2. What about here? Instead of n, I want it to be n minus 2. So I'm going to put, where there is n, you put n minus 2 because that's what I want. But you retain this, the lowest power of x. So we are going to substitute, make a substitution in the first term, or simply the first series, and the third series on the left-hand side. So remember, everywhere here in the first series, we are going to substitute n with n minus 2. And everywhere in the third series, we are going to substitute n with n minus 3. So this is what we have. So what we are calling is shift the index. Shift the index in the first and third summations. I've told you what we do in the first and what we need to do in the third. So in the first, what will we have? And remember here, everywhere where there is n here, it will be n minus 2. So it's like we have n minus 2 is equals to 1. When I take negative 2 to the right, we have n is equals to 3. And here, instead of n, now we will talk of n minus 3. So n minus 3 is equals to 0. So what is n? N is equals to 3. So I hope that is clear to everyone. So the first summation will be now from n is equals to 3 to infinity. I hope I've explained how to get that. Because where there is n, I'm putting n minus 2. So n minus 2 is equals to 1. When you make n the subject, you get n is equals to 3. Instead of n squared, where there is n, you put n minus 2. So it will be n minus 2 squared. A subscript n minus 2, then x raised to n minus 2. I've replaced every n in the first summation. The second summation, we return it. The sum from n is equals to 2 to infinity n minus 1, a subscript n, x raised to n minus 2. But the third one, the third summation, I'm replacing n by n minus 3. So this will be n is equals to 3 to infinity a sub n minus 3 x raised to n minus 2. That should give us 0. See what we have done? We have shifted the index in the first and the third summation. So you can see now the powers of x, they are the same. Everything is x raised to n minus 2. Now, what next? I need to combine these three summation into one summation. But for us to combine them, we must ensure that they start from the same index. Look at here, it's starting from n is equals to 3. Again, here, so it is easy to combine those two. But this one starts from n is equals to 2. You must ensure that you start from n is equals to 3. So I'll find the first term here. Then it means the next term going onwards will now be from n is equals to 3 all the way up to infinity. So this thing can be written as, you can write over the sum for n is equals to 3 to infinity, n minus 2 squared, a n minus 2, x raised to n minus 2. Then the other one, we will have a plus. When I put n is equals to 2 here, everywhere you see n, put n is equals to 2. What do we get? We are going to get 2 times 2 minus 1. That's 2 times 1, which is 2. So I'm going to get 2 times a2 times x raised to 0. That's when n is equals to 2. So it means the next term now we start from n is equals to 3 up to infinity. So n is equals to 3 to infinity, n minus 1, a sub n, x raised to n minus 2. Then the other series is the sum from n is equals to 3 to infinity, a n minus 3, x raised to n minus 2 is equals to. Now you see we can combine these three summations because they start from the same index, that is n is equals to 3 all the way up to infinity, and they have the same power of x. So we combine the summations into one. Combine the summations into just one summation. Into, well, let me just say combine the summation. There's no need of writing so many other things. Combine the summations. So when you combine this, what you're going to get, it will be equal to the sum from n is equals to 3 to infinity. Let's start with the first one. I have n minus 2 squared times a n minus 2. Then the other one, I'm through with this one. Let's go to this. So I'll have a plus n into n minus 1 an. Then the third summation is now a minus an minus 3. So all this will multiply x raised to n minus 2. Then you see this one will be plus 2a2 x raised to 0. That should give us 0. So once you're through with this, now equate the corresponding powers of x. So equate the corresponding coefficients. You see here we have 0x raised to 0 plus 0x raised to n minus 2. Because the right hand side is 0, so I'm just writing so that you can see what is happening. I don't need to write that. So let me just rub it. So let's start with the powers of x raised to 0. X naught, or the coefficient of x naught, what are we going to get? So you write coefficient of x naught, or simply x raised to 0. On the left, we have 2a2. On the right is equals to 0. So from here, it simply means that when I solve for a2, it means a2 should be equal to 0. So that's what we have found, as the value of a2 is very important. What about the coefficients of x raised to n minus 2? It is the whole of this one that we need to equate to 0. Everything here, equate it to 0. So we are going to talk of, let me use another color, n minus 2 squared times a substitute n minus 2 plus n minus 1 an minus 3 is equals to 0. So I can now be able to make a subscript n the subject of the formula. So you can just say, or if you make a subscript n the subject, you are going to get, let's start with this one, an minus 3, then minus n minus 2 squared times an minus 2. And everything here, you need to divide by n times n minus 1. So look at the equation that you have formed there. That equation has a special name. Let me bracket it and then I tell you what it is referred to as. This equation is called a recurrence relation. Recurrence relation. Recurrence relation for that given ODE. Remember, the recurrence relations are different depending on the ODE that you're being given. Now, that recurrence relation is used to find the series coefficients. But starting from n is equals to, look at where we got it from. This recurrence relation is valid for n is equals to 3, 4, 5, etc. Because we got it from the series that was starting from n is equals to 3 up to infinity. Of course, the index cannot be negative. That's why we are starting from 3. You see, when you put n is equals to 2, you are going to get here where we have, if you put n is equals to 2, it means this will give you a subscript 2 minus 3, which is a subscript negative 1. And the index cannot be negative. So you have to start from 3 going onwards. Hope that is clear to everyone. Now, let's start with n is equals to 3. So when I put n is equals to 3, what am I going to get? I'm going to get a3 is equals to, well, let me use black. I am going to get a3 is equals to a naught minus a1 everything over 6, which is the same as 1 over 6 a naught minus 1 over 6 a1. Is it 6? We are putting 3. 3 times 2, that is 6. Let's also try with n is equals to 4. So when I substitute, you can write here, put n is equals to 4. So let's see what we are going to get. That will give us a4. So you say a4 is equals to Now it will be A1 minus. Now 4 minus 2, that is 2. When you square it, that is 4 times A2. Everything you divide by, that will be 2, that will be 4 times 3, that is 12. And so this thing can be written as 1 over 12 A1 minus 4 over 12, which is 1 over 3 A2. Hope that is clear. Maybe you can try when n is 5. So you can say put n is equals to 5. What are we going to get? We're going to get A5 is equals to, but before I write the solution for A5, look at our value of A2. We said A2 is equals to 0. That's what we got from here. So it's better I simplify. Where there is A2, just put 0. So this is 0. Somebody will ask, why is it 0? I've explained. A2 is 0, so this is the same as 1 over 12 A1. So remember, I don't know A0, I don't know A1. Let's get A5. It will be A2 minus. Now 5 minus 2, that is 3 squared, that will be 9. A3. Then everything you divide by, let's see, that is, we are substituting 5. So 5 times 4, that will give us 20. Now, once we substitute that, we need to simplify. So when we simplify this will give us, let me write it here. But remember, A2 is 0, so it's better I cancel this to be 0. So I simply have 9 over 20. Remember, it was 5 times 4, which is 20. So this negative 9 over 20 A3. But the question is, what is A3? A3, we have the value here. So we replace it by what we got here. So that's the same as negative 9 over 20 times 1 over 6 A0 minus 1 over 6 A1. So what do we get? Let's work it out. In fact, let me just write this side. So that should give us, you can use this color, negative 9 over 20 times 1 over 6. That will give us negative 3 over 40. Of course, I've simplified. 3 over 40 A0. Then the other one is plus 3 over 40 A1. That's clear. Now, remember, you can go all the way up to infinity, but we just need to know how the series starts. So the first few coefficients will tell us how the series starts. So now that we know the coefficient, we now go back to the solution. So you can say hence, the general solution is look at where we started. We said y is equals to the sum from n is equals to 0 to infinity an x raised to n. That's where we started with. And if you break it down, it's the same as a0 plus a1x plus a2x squared plus a3x cubed plus a4 x raised to 4 plus a5 x raised to 5. You see, there are so many other terms, so I cannot write everything. Just say plus so many other terms. But I know a2 is equals to 0, so this term will vanish because a2 is 0. Do we know a0? No. Do we know a1? No. So you can say or y is equals to a0 plus a1x, a2 is 0, so we go to a3. But we know a3 in terms of a1 and a0. That will 1 over 6 a0 minus 1 over 6 a1. So you write here plus 1 over 6 a0 minus 1 over 6 a1. This is times x cubed. A4, do we have it? Yes, plus 1 over 12 a1 x raised to 4. What about a5? We have the value here. It was negative 3 over 40 a0 plus 3 over 40 a1. So I'll have here a plus negative 3 over 40 a0 plus 3 over 40 a1 x raised to 5 plus so many other terms. You can't write everything. Now, I can decide to group the a0s together. Let's start with a0s. Then here we have 1, those with a0 only. So here we'll have x cubed over 6. The other one will give us negative 3x raised to 5 over 40. Those are the ones with the a0. Remember, there are so many other terms which we left out, so I can just write plus so many other terms. Then what about those with a1? A1, we have x. The other one is negative x cubed over 6. Another one is x raised to 4 over 12. X raised to 4 over 12. And I can see another one with a1 is 3 over 40. So 3x raised to 5 over 40. Remember, there are so many other terms, so I can just write plus so many other terms. And so this is our solution. This can be written as, this is the same as, you can just say, or y is equals to a0 y1 plus a1 times y2. Where what I'm calling y1 is this one here. And what I'm calling y2 is this other bracket. So you see y1 is a solution, y2 is a solution, and now y is a linear combination of those two solutions. A0 and a1 are arbitrary constants. So you can just say where a0 and a1, these are arbitrary constants. The y1 and y2 are two independent solutions of the given ODE. Now that is part A. Remember, when we talk of power series solution, this series that you have found, it is not the exact solution. It is an approximate solution. So power series is usually used to approximate the solution of an ODE. And you see, somebody might be asking, why did we get x raised n is equals to 6, n is equals to 7? You see, there are so many terms which you cannot write all of them. But you simply want to know how the series starts so that you see how the solution looks like. And so when you talk of power series solution, you realize that our functions y1 and y2 are polynomials. So power series solution is used to solve the ODE in terms of a polynomial. Give the solution to that equation in terms of a polynomial. Having explained those concepts, let's look at part B. Part B, I'm going to write the same ODE again. Our ODE is 2x squared d squared y dx squared, then minus x dy dx, plus x minus 5 times y is equals to 0. Remember, again, we want a series in powers of x. We said x naught is equals to 0. So in this case, the solution is that we said x naught. In this case, our x naught must be equal to 0. So you need to ask yourself, even before you proceed to solve the ODE, you need to know whether is 0, is it an ordinary point or is it a singular point? And if it is a singular point, is it regular or is it irregular? Look at here. Look at 2x squared. If I substitute x is equals to 0, I'm going to get 0. So it means the point x naught is equals to 0 is a singular point. And you need to test, is it regular or irregular? So this point is, of course, if you test, you'll find that it is a regular singular point. Regular singular point of the ODE. Now, it's like we are solving this ODE about a regular singular point. And the method that is used in such solution, solving such kind of equations, is what we call the method of Frobenius method. So, use Frobenius method. What does it entail? Frobenius method. Now, what will be the solution? So you say let our solution y to be equal to the sum from n is equals to 0 to infinity a subscript n x minus x naught raised to n, but now you add r, a real number r. But you see, we have said x naught is equals to 0, so you can say put x naught is equals to 0 to get y is equals to the sum from n is equals to 0 to infinity a n x raised to n plus r, and a naught cannot be equal to 0. So this is our assumed solution. Our solution should be in the form of this kind of a series. Because it is a solution, it must satisfy the given ODE. And I said R here is a real number. R belongs to the set of real numbers. Now, also R is a real number. Now let's find the derivatives of this solution. So you can just say that therefore dy dx, what is it? It is the same as the sum from n is equals to 0 to infinity n plus r. Remember me, I'm using power rule. N plus r a sub n x raised to n plus r minus 1. And the other derivative, d squared y dx squared, is the same as the sum from n is equals to 0 to infinity n plus r times n plus r minus 1 a subscript n x raised to n plus r minus 2. I have used power rule of differentiation. to find those derivatives. Now, let's substitute them into the ODE because they are this is a solution of the ODE, so it must satisfy the ODE. So when we substitute back to that ODE, we are going to get this. So substitute into the ODE to get into the ODE to get. So we are going to get, the first term is 2x squared. So we have 2x squared times the second derivative, which we have found to be the sum from n is equals to 0 to infinity, n plus r, n plus r minus 1, an x raised to n plus r minus 2. Then minus x, first derivative, we have found the sum from n is 0 to infinity, n plus r, an x raised to n plus r minus 1. Then the other one is plus x minus 5 times our y, which we said is the same as sum from n 0 to infinity, an x raised to n plus r. That should give us 0. So that should give us 0. Now we need to simplify this. By simplifying, I mean you take these coefficients inside. Even this, you need to take it inside. Even the whole of this, you need to take it inside. So what are we going to get? Let's see. The first one will give us the sum from n is equals to 0 to infinity, 2 into n plus r, n plus r minus 1, a subscript n, then x raised to n plus r. Remember, loss of indices, we are multiplying x squared and x raised to n plus r minus 2. So when you add the powers, you get n plus r. The second summation, we are going to have minus the sum from n is equals to 0 to infinity, n plus r, multiplying a sub n, then times x raised to n plus r. Again, loss of indices, remember here it is x raised to 1. Then the other one is a plus. It will be plus. So this one, of course, that will give rise to two terms. Let's start by multiplying by x so that we get the sum from n is equals to 0 to infinity, a sub n, x raised to n plus r plus 1. I've multiplied that by x. Then now times -5, we'll have minus. Let me take this to the left. We'll have minus this sum from n is equals to 0 to infinity, 5a sub n, x raised to n plus r, and the right-hand side should be equal to 0. Now look at these summations. There are how many? There are 4. Combine those with the same power of x. So I can see 3 of them have the same power. This one, this, and the last one, this one. So we are going to combine those 3. So we combine the series with the same power of x. So you can write here, combine the series with the same power of x. So this is what we are going to have. We are going to have the sum from n is equals to 0 to infinity. Here we have 2 n plus r, n plus r minus 1. The other one is minus n plus r, And the last one is minus 5. The all of this should multiply a subscript n times x raised to n plus r. Then the other series is a plus the sum from n is equals to 0 to infinity an x raised to n plus r minus, no, that's a plus 1. The right hand side we need to get 0. So you see what I've done? You simplify as much as possible. By simplifying, in this case, we have combined those series with the same power of x. Is it possible to simplify the first series? Look at this. We can be able to simplify this because I can see n plus r is common. Let's see. If I factor out n plus r, what am I going to get? It will be n plus r. Let me use another color. The black is fine. So black, that will give us n plus r outside. So that inside here, I'll have 2n plus 2r minus 2, then minus 1. Then I can see this minus 5. And that will be 2n plus 2r minus 3. So I can rewrite this in the simplest form. So we have or the sum from n is equals to 0 to infinity. Here we have n plus r times 2n plus 2r minus 3. Then you subtract 5. This should multiply a sub n x raised to n plus r. Then plus the other summation, that is the sum from n is equals to 0 to infinity, a sub n x raised to n plus r plus 1. And so that should give us 0 on the right-hand side. So once you're there, we now need to shift the index. Look at, why are we shifting the index? It is because those powers of x are not the same, and we cannot simplify what we have further. So we are only left with the option of shifting the index so that we can be able to combine these two summations into one summation. So, and I told you, you need to shift to the lower power of x. The lower power of x is n plus r. So I need to shift this. Instead of n plus r plus 1, how do we make it n plus r? So here, I need to put n is equals to n minus 1, because when I subtract 1 from n, I'll get n plus r. So wherever there is n in the second summation, we are going to substitute that by n minus 1. So you write shift the index in the second summation. I've told you what to do. Where there is n, you substitute n minus 1. So that this is what you're going to get. It will now be the sum from n is equals to 0 to infinity, n plus r, 2n plus 2r minus 3, then minus 5. This should multiply an times x raised to n plus r, then plus, everywhere you see n, you put n minus 1. So you see, when I substitute here n minus 1 is equals to 0, that means n will be equal to 1. I hope that is clear. So this one should now start from n is equals to 1 to infinity, a subscript n minus 1 times x raised to n plus r. That should give us 0. I hope that is clear. So now you see the powers of x are the same. So what you do, you can now combine these two summations, but it is not possible because Look at the first summation starting from index 0. The second summation starts from index 1. You must ensure that they are starting from the same index. So I have to ensure that the first summation should start from index 1 so that I can combine it with the second summation. So what I'll do, I'll be able to evaluate the first term in the first summation so that the second term going onwards will start from index 1. So what we do is this one, we put n is equals to 0 in the first summation. Here, put n is equals to 0. So that can be written as, when I put 0, I'm going to get this. I'm going to get r. Then the other one is 2r minus 3 minus 5 should multiply n naught, then x raised to r. So now it means the second term going onwards will now start from n is equals to 1. So plus n is equals to, the sum from n is equals to 1 to infinity, n plus r, 2n plus 2r minus 3, then minus 5. This should now multiply an x raised to n plus r. Then I can see the other one is plus, and the sum from n is equals to 1 to infinity, an minus 1 x raised to n plus r is equals to 0. So now you see we can combine these two, because look at the index, it is 1, here it is also 1, and they have the same power of x. Those are the conditions that must be satisfied for you to combine any two summations. So when I combine these, I can just write or, even here, or this you could write as 2r squared minus 3r minus 5 times a naught times x raised to r, then plus the sum from n is equals to 1 to infinity. We are now adding them, combining them. So here the first one is n plus r. That is 2n plus 2r, 2n plus 2r minus 3 minus 5. They should multiply an plus the other one is an minus 1 times x raised to n plus r is equals to 0. So that's what we have. And now the next thing is, now you equate the corresponding coefficients. So we write this, that equate the coefficients of the corresponding powers of x. Equate the corresponding coefficients. Let's start with the coefficients of x raised to r. So you could write here coefficients of x raised to r. What are we going to get? Let's see. It will be 2r squared minus 3r minus 5. This should multiply a naught. And on the right hand side, everything is 0, so we get this to 0. But we said a naught is not equal to 0. So you can say but a naught is not equal to 0. Now, let me explain this before I can solve it. This thing that we have formed, this equation, this is called an indicial equation. Let me write it here. It is called an indicial equation. It is the equation that corresponds to the lower power of x, the coefficient of the lower power of x. That's called an indicial equation. And we said a naught is not equal to 0, so therefore it means that the other one is 0, so 2r squared minus 3r minus 5 must be equal to 0. So what are the roots when you solve it? That's a quadratic equation in R, which you know how to solve. Use any formula of solving quadratic equation. So when you solve it, you get the roots to be R is -1 and R is 5/2. R is equals to -1, because there are two solutions. Another one is R is equals to 5/2. I hope you know how to solve quadratic equations. Now we are done with the coefficient of the x raised to r. Let's see the coefficient of x raised to n plus r. So right here, coefficient of x raised to n plus r. What are we going to get? It is n plus r times 2n plus 2r minus 3 minus 5. This should multiply an, then plus an minus 1. On the right hand side, it should be equal to 0. So let me make a substituent the subject. So from here, we can as well say that therefore a subscript n is the same as, because I'll take the other to the right hand side and then divide by the coefficient of a subscript n, so that we are going to get -1 over n plus r times 2n plus 2r minus 3, then minus 5. This should multiply an minus 1. What did I do? I took this to the right hand side to get the negative. That's why we have -1 there. Then you divide by the whole of this. So what we get here is another relation, what we are calling the recurrence relation. So let me bracket it and then I comment on it. This is called a recurrence relation. Recurrence relation. This will help you find the series coefficients. And now this is valid. This relation is valid for all n. N must start from 1 going onwards. 1, 2, 3, 4, etc. You could go up to maybe 4 is okay. There are so many other terms up to infinity. So that's a recurrence relation. Now let's find those other coefficients, series coefficients. If I put n is 1, what am I going to get? If I put n is 2, what am I going to get? In that manner. So we make such substitution just to know how the series starts. So here, remember we had two values of r, so we are going to consider two cases when r is -1 and also when r is equals to 5/2. So let me write here that case 1, is when r is equals to -1. So you can write when r is equals to -1. What will happen? How will the recurrence relation look like? So when I substitute into our recurrence relation, we are going to get this. We are going to get a subscript n is equals to -1. That's -1. You need to divide this by, while there is r, I'm putting -1. So this will be n minus 1 into, there now we'll have 2n minus 5. I hope that's clear because it is -2 minus 3. Then there's another minus 5 times a subscript n minus 1. That is what we get. And remember, n is greater or equal to 1. N is a natural number which is greater or equal to 1. So with this now, when I put, you can say put n is equals to 1, what do we get? When n is equals to 1, I'm going to get a1 is equals to -1 over 1 minus 1 is 0. Then that will be 2 minus 5, then minus 5 times a naught, which is the same as 1 over 5 times a naught. That's what we get. What about when n is equals to 2? What are we going to get? So you write here, put n is equals to 2. N is equals to 2. We are going to get a2 is equals to -1. That should be -1 divided by, let me take this up. So now n minus 1, that will give us 2 minus 1, which is 1, times 4 minus 5, that's -1. Then again minus 5 times a1. And so denominator, that's -1 minus 5, that's -6. -1 over -6, that's 1 over 6. 1 over 6, a1. But do we know a1? Yes, it is 1 over 5 a naught. So this is the same as 1 over 6 times 1 over 5 a naught, which is simply equal to 1 over 30 a naught. That's what we have as a2. We can find a3 and a4. So let's say put n is equals to 3. So that will give us a3 is equals to -1 over. Now here we'll have 2. That's 6 minus 5, that is 1. Then again minus 5. Here we'll have a2. And so when you work it out, 2 minus 5 is -3. So that will give us 1 over 3. 1 over 3 a2. But I know a2 as 1 over 30 a naught. So this will give us 1 over 3. Our a2 is 1 over 30 a naught. And so when you multiply, you get 1 over 90 times a naught. There's, as long as we know how the series starts, there's no need of calculating the other higher values of n. So we can stop there for this case and then therefore say that our solution corresponding to this value of r is given by, so you can just say hence the solution corresponding to r is equals to -1. Let me write that in a proper manner. Corresponding to r is equals to -1 is, we will call it y1, because you see we have two cases. So for the first case, we call it y1, and for the other one, we call it y2. So you will say here that y1 is equals to mean y for the case 1 is equals to the sum from n is equals to 0 to infinity of an x raised to n plus r. But r is -1, so this is the same as the sum from n is equals to 0 to infinity an x raised to n minus 1, because r is -1. And so this thing can be written as x raised to -1 times the sum from n is equals to 0 to infinity an x raised to n. You see, I've factored out x raised to -1 because it does not depend on n. And so this can as well be written as x raised to -1 times a naught plus a1x plus a2x squared plus a3x cubed plus so many other terms up to infinity. And now we can replace those coefficients. So this is the same as writing x raised to -1 times, what was our a naught? I don't know. So just leave us a naught. What about a1? We got it as 1 over 5 a naught. Let's just confirm. So a1 was 1 over 5 a naught x. A2, what did we get? It was 1 over 30 a naught. 1 over 30 a naught x squared. The other one is 1 over 90. 1 over 90 a naught x cubed plus so many other terms. You could go up to a4, a5, etc. But to save on time, as long as you know how the series starts, then that will be, because this is an appropriate, so the not appropriate, but approximate solution. So it will not give you the exact solution. So let me factor out a naught. A naught times x raised to -1 times 1 plus x over 5. Then here we have x squared over 30 the other one is x cubed over 90 plus so many other terms. So now we can say now let a naught be equal to 1. So you can just say put a naught is equals to 1, so that you can get rid of that. Because it's a constant different from 0. So therefore y1 will be equal to, now we'll have x raised to -1 times 1 plus x over 5 plus x squared over 30 plus x cubed over 90 plus so many other terms. That is the solution corresponding to case 1. Let's look at case 2, where r is equals to 5 over 2. So I'll write the same. We do the same thing. So I write here case 2. In this case, you can write when r is equals to 5 over 2. What will be an, the recurrence relation? How will it look like when you substitute r is equals to 5 over 2? Let me take you back to the recurrence relation where we need to substitute. It is this one. So here where there's r, you put 5 over 2. So let's go back and replace it. See what you're going to get. So that will give us -1 in the numerator over n plus r. Remember it is n plus now 5 over 2 times 2n plus 2r. That will be 5. 2r, remember r is 5 over 2. So 2 times 5 over 2 will give you 5. So I'll write here plus 5. And it was minus 3. Then there's another minus 5. an minus 1. Of which, if you simplify this further, what are we going to get? It will give us -1 in the numerator, -1 over n plus 5 over 2, and they should multiply 2n plus 2, then minus 5 times an minus 1. And so from here, I can factor out 2 so that I'll have 2 into n plus 1. And so the 2 will multiply this. We'll multiply the first bracket. So we are going to get this. It is the same as -1 over 2 into n plus 5 over 2 times n plus 1. I've factored out 2, then minus 5 times a raised to n minus 1. And so when I take the 2 inside that bracket, what will we get? Let's see. Take it inside here. We are going to get, this will now be equal to -1 over 2n plus 5 times n plus 1. Let me write that in a proper manner. N plus 1 minus 5 times a sub n minus 1. You can just say or an is equals to that. So this is the recurrence relation when you substitute r is equals to 5 over 2. And so here is valid for n greater or equal to 1. N is a natural number. In this case, it is greater or equal to 1. So let's now see, when I put n is equals to 1, what are we going to get? So right here, put n is equals to 1. What are we going to get? We are going to get a1 is equals to -1 divided by, now here we'll have 7 because it is 2 times 1 plus 5. So that will give us 7 times 2 minus 5 a naught, which is the same as 14 minus 5 is 9. So -1 over 9 a naught. That's what we find. What about when n is equals to 2? Try with 2, so you write put n is equals to 2. What are we going to get? It will be a2. Let me use another color. That will be a2 is equals to -1 over. So there we'll have 2 times 2, that's 4 plus 5 is 9 times 3, then minus 5, a1. And so that's the same as 27 minus 5 is 22. So that's -1 over 22, a1. But you see, we know the value of a1, so we can replace it because a1 is the same as -1 over 9 a naught. So this -1 over 22 times -1 over 9 a naught. Multiply 22 times 9. What will that give you? That's 198. So it's 1 over 198 a naught. And we can try with 3. Put n is equals to 3. Let's see what you're going to get. It will be a3 is equals to -1 over, that is 6 plus 5, that should give us 11. And remember it is 3 plus 1, so that would be 4. Then there's -5 times a2. And so when I work it out, what do we get? We'll get 44 minus 5, that's 39. There will be -1 over 39. -1 over 39 a2. But we know the value of a2, so we can replace that by what we got. So this is the same as -1 over 39. Our a2 was 1 over 198 a naught. When you multiply 39 times 198, you get 7722, 7722. So this -1 over 7722 a naught. And so now the solution corresponding to the second case is given by y2. Remember, the one that was corresponding to the first case was y1. This other one, we are going to call it y2. So you can just say hence, and the solution corresponding to this second case, that is r is equals to 5 over 2, is given by, we are going to call it y2. y2 is equals to the sum from n0 to infinity an x raised to n plus r. This is n. But r is 5 over 2. So this can be written as the sum from n is equals to 0 to infinity an times x raised to n plus 5 over 2, which you can as well write as x raised to 5 over 2 times the sum from n is 0 to infinity an x raised to n. And so let's also expand this. This is the same as x raised to 5 over 2 times a naught plus a1x plus a2x squared plus a3x cubed plus so many other terms. Let's replace those constants. So this will be equal to x raised to 5 over 2 times, I don't know a naught, let's return it, but we know a1. What did we get as our a1? It was negative 1 over 20, no, negative 1 over 9 a naught. Negative 1 over 9 a naught x. The other one is negative 1 over 22. Remember, that is a2. Let's check. A1 was negative 1 over 9. We don't know a naught. A2, we have found positive 1 over 198. So let me replace it here. It was positive 1 over 198. So I'll rub what I've written here and replace it with the positive 1 over 198. So I rub everything, not everything, but just what I'd written as negative 1 over 22. That should be positive 1 over 198. So then the next is a3, which we got negative 1 over 7722 a naught. 1 over 7722 a naught. That will be x cubed plus so many other terms. And you see a naught is common, that can be factored out. So we'll write a naught x raised to 5 over 2. Here now we'll have 1 minus x over 9, that's x over 9, plus x squared over 198 minus x cubed over 7722. This is 7722. Remember, there are so many other terms up to infinity, so plus so many other terms. And again, you substitute a naught is equals to 1, so you can write put a naught is equals to 1. A naught should be equal to 1. We said a naught is a constant different from 0. So when we substitute 1, we are going to say that therefore y2 is equals to x raised to 5 over 2 into 1 minus x over 9 plus x squared over 198 minus x cubed over 7722 plus so many other terms. So this y2 is the solution corresponding to case 2. And so it is independent from the solution that we got in the first case. So let me bracket these two solutions. This one, this was y1. And the other one is y2, which is independent from y1. So I also bracket this. Now the question is, how do you get the general solution? So general solution is now very simple. So you write general solution is given by let me use another color, that's red. Y is equals to an arbitrary constant C1 times Y1 plus another arbitrary constant C2 times Y2. C1 and C2 are arbitrary constants, so this is how to find the general solution of such kind of an ODE, where you are solving about a regular singular point. You know Y1, you know Y2, you can replace them. In place of Y1, you write what we found, and in place of Y2, you can write what we found. And so that's the general solution, where C1 and C2 are arbitrary constants. So thank you all for watching this video. Please subscribe to my YouTube channel, that is Professor Francis Okech. When you go to the YouTube search, type Francis Okech or Prof. Francis Okech, and you will find me right there. Also, don't forget to comment, like, and share this video. When we meet next time, we look at more problems involving power series solution of linear ODEs. Bye-bye.